Okay, here's the second half of our equilibrium discussion. The first half was Le Chatelier's principle. The second half is more quantitative considerations with equilibrium. My apologies for getting this video out late. I've been having all kinds of hardware issues here making videos. Anyway, for any reaction where these small letters represent the coefficients in the balanced reaction, you can set up what's called a reaction quotient, Q. Q takes this form. It's always the products on top, the reactants on the bottom. You raise the concentration of each product to the power that relates to the coefficient in the balanced equation. These little brackets that you're seeing here, those brackets represent molarity. So this would be the molarity of chemical D raised to this power. That power, again, is taken from the coefficient. So that's an equilibrium expression. Older books, you'll hear it called the law of mass action. So the equilibrium expression there. You can write that for any equation. Things to keep in mind. Again, the brackets represent molar concentrations, and also representing concentrations. We can represent concentrations as either molarity or partial pressure. Traditionally in chemistry, things that are in aqueous solution, anything that's aqueous, we're going to represent the concentration with molarity. Things that exist as gases, we traditionally represent those with partial pressures. We just put a big P, so you'd have like partial pressure of NH3. Because the partial pressure of a gas is directly related to its concentration. So, real quick exercise here, the easy stuff in this section, writing these reaction quotients. For this equation here, this is the reaction that gives us ammonia gas. Oh, you'd say the reaction quotient Q, products over reactants. The product is ammonia, so it's going to be the partial pressure of ammonia raised to the second power. I like to put everything in parentheses, just easier on my brain. So that's your product, ammonia, raise it to the second power, over the partial pressure of hydrogen gas cubed. So you have the partial pressure of your hydrogen gas cubed times the partial pressure of your nitrogen gas. And again, because the coefficient in front of nitrogen is a 1, it's just the partial pressure of the nitrogen gas raised to the first power. So for this one down here, since everything's aqueous, we would want to write the concentrations using molarity. That's going to be the molarity of the bicarbonate ion, molarity of your HCO3 to the -1 power, times the molarity of your H+, all over the molarity of your H2CO3. That's your carbonic acid there. H+, sometimes you'll hear it called the proton. So that's writing some simple equilibrium expressions. Now, if you look at the next couple of examples, you have solid zinc oxide reacting with gaseous carbon monoxide produces liquid zinc and carbon dioxide gas. It's the products, these guys, over the reactants. But remember what we said about equilibrium? Things that appear as a liquid don't really play into the equilibrium position. Solids don't play. Best way of thinking of it is pretend that any liquid has a concentration of 1. Any solid has a concentration of 1. So if you thought of it that way, you'd say, okay, for this one it's going to be the partial pressure of your CO2, partial pressure of your CO2, times whatever concentration you want to use for the zinc liquid. But we said, hey, anything that's a liquid, pretend it's a 1. Partial pressure of your CO times, oh, what are we using for the concentration of a solid? 1. So basically for this one here, Q is going to be the partial pressure of the CO2 all over the partial pressure of the CO. Again, liquids and solids don't really count. You treat a liquid or a solid as just being the number 1. So for this one here, solid barium phosphate dissociates, gives you this times, so it's going to be the concentration of this stuff, the barium ions, to the 3rd power, times the concentration of the phosphate ions to the 2nd power, all over the, oh wait, that's going to be over a 1. Oh geez. Yeah, Q here is going to be your molarity of your barium ions to the 3rd power, molarity of your phosphate ions to the 2nd power. Again, solids, treat them as the number 1. So, let's see. Let's talk about the equilibrium constant, K. It turns out the concentrations in a reaction will keep changing until the number Q hits some number and it doesn't change anymore, and that is when the reaction is at equilibrium. And at that point, Q is equal to K. The reaction quotient, Q, is equal to K when the reaction is at equilibrium. Basically what that means to you as a chemist, if you're cooking something up, you threw everything into a pot, you started letting things react, they keep reacting, the concentrations are changing. When the concentrations aren't changing anymore, it means you have hit equilibrium. So when those concentrations are no longer changing, you are at equilibrium, and at that point the equilibrium, or at that point the reaction quotient Q is equal to K. Quick example of the importance of the equilibrium constant. It's kind of hard to wrap your brain around sometimes, and it's not immediately obvious how they ever figured this out, but let's look at a simple reaction. You have dinitrogen tetroxide. It dissociates to give two molecules of nitrogen dioxide. If you start this reaction under different conditions, say you started it with your flask, you have a flask and you start with the partial pressure of N2O4 as 1 atmosphere. The partial pressure of the nitrogen dioxide, none. So you're just putting in pure N2O4. You let it hit equilibrium. You'll end up with these concentrations. You'll get to this situation with these concentrations and nothing's going to happen anymore. It's just going to stop. Okay, well, what if we did just the opposite? Instead of starting with pure N2O4, we start with pure NO2 in our flask. So that would be this second case here. So we start with pure NO2. Hey, some of that NO2 is going to react, giving us N2O4. That should have an equilibrium arrow. It's going to keep doing it until it hits these concentrations. Once you get to these concentrations, the reaction is done. These concentrations are not going to change. You've hit equilibrium. You could start it with 1 atmosphere of each. The reaction is going to continue until you get to these concentrations. Now, the equilibrium expression here is K would be the partial pressure of your NO2 squared all over partial pressure of your N2O4. Now, here's the weird thing. If you take these numbers and plug them in here, so for the partial pressure of the NO2, if I plug in 1.56 and I square it, and then for the N2O4 I plug in 0.22, I come up with a number 11. Hey, if I take these concentrations, I plug in 0.88 and I square it. And for the concentration of my N2O4, I plug in 0.07 and I do the math, I end up with 11. In this situation here, guess what? You plug those numbers in, you get 11. So even though the final situation in each flask is completely different, they have different concentrations of things, the reaction goes, the concentrations change, the concentration of these two things will change until it gets to a ratio where you get 11 from that equation. So the equilibrium expression kind of rules a reaction. It tells you where the reaction's going, what the final concentrations of things are going to be based on this constant, the equilibrium constant, K. So that's your equilibrium constant, and it tells you an awful lot about a reaction. Let's take a closer look at these equilibrium constants. So values of K, they're never negative. Will never, never, never have a negative value of K. They can be incredibly small, like 1 times 10 to the negative 100th power. It's still not a negative number. It's really dang close to 0. 10 to the negative 100th power is way close to 0, but it's not 0, and it's not ever going to cross 0 into negative territory. You can have values of K that are incredibly large, up to, 10. I've seen them go up as high as 10 to the 100th power. Here's what the value of K means for you. If your value of K is large, it means that the equilibrium lies to the right. And it means that when that reaction's done, you're going to have mostly product. If your value of K is small, it means the equilibrium lies to the left. And that means when you're done, you have mostly starting materials. Remember, it goes, you have reactants, turning into products, and it's reversible. So a large value of K means when the reaction's done, you got almost all products. A small value of K means when you're all done, you have mostly reactants. If K is kind of middling, it's like, 5 or 1/2 or something, it means when the thing hits equilibrium, you got a god-awful mess. You got a god-awful mixture of reactants and products all in the same flask. We hate situations like that because then you have to separate stuff. Anyway, you have to learn how to manipulate a reaction on paper, and as you manipulate that reaction, it turns out the value of K changes. So let's take a quick look here. Here's that reaction we talked about previously that gives us ammonia. At a certain temperature, be aware of that. The one thing that will affect the value of K is temperature. It's a constant at a certain temperature. So at a certain temperature, K has one value. You heat the reaction up, K has a different value. So K depends on temperature. Oddly, it also depends. The numerical value also depends on the coefficients in the balanced equation. You can manipulate reactions mathematically on paper. You might remember this from Chem 1 in thermodynamics. Sometimes you'll have a reaction and you'll multiply all these coefficients through by something. If I were to multiply all of these coefficients here by 2 2 times 3 gives me 6. 2 times 1 gives me 2. 2 times 2 gives me 4. So now instead of saying 3 moles of hydrogen, 1 mole of nitrogen gives me 2 moles of ammonia, I'm saying 6 moles of this react with 2 moles of this to give me 4 moles of this. Guess what? That changed the value of K. Now, it doesn't work the way you might assume. You might think, oh yeah, I'll just take the value of K and multiply by. No. If you multiply coefficients through, you raise K to that power. So to get from here to here, I had to multiply by 2. What's the new value of K? 6 times 10 to the negative second power squared, which gives me 3.6 times 10 to the negative third power. What if I take this reaction here and I divide it by 3? So if I divide by 3, that becomes a 1. Divide this coefficient by 3, it becomes 1/3. Divide this by 2/3. What's my value of K? It's going to be 6 times 10 to the negative second power. I divided by 3. How do I raise it? Oh, I raise it to the 1/3 power. And the new value of K is 0.392. So whatever you do to a reaction when you're multiplying or dividing, multiply through, you raise it to that power. You divide through, you raise it to the fractional power. What if you take a reaction and you write it backwards? What if I take this reaction and I flip it? Don't make the naive mistake of thinking, oh, you write it backwards, you change the sign of K. You never change the sign of K. Remember, K will never be a negative value. It's got to be a positive number. So here's the deal. If you take a reaction and you write it backwards, you take the reciprocal of K. And we show you that on the next page here. So if I take that reaction and I write it backwards, K is now going to be 1 over the 6. What was the value there I had? 6 times 10. And that's going to give me 16.7. So if you flip the reaction so it's reading backwards, you take the reciprocal. What you see that I just did there is I went from here, I took that reaction and I flipped it. So it's reading backwards. When you flip it, you end up taking the reciprocal of K. Last thing you have to know about K is you can add reactions together. You might remember from thermodynamics last semester, you added reactions together. And when you added up your reactions, you added up your values of delta H. Well, guess what? You don't add values of K, you multiply them together. So if I have these two reactions, this first reaction is carbonic acid dissociates into a proton and a bicarbonate ion, has this value of K. Real quick, that 10 to the negative 7th, what do you think that means? Does that mean the equilibrium lies mostly towards products or mostly towards starting material? Carbonic acid is a real weak acid, so if you have a solution of carbonic acid, most of it exists as this stuff. And a very, very small fraction will exist as H plus and HCO3 minus 1. So small value means the equilibrium really lies that away. I guess I should put my arrows in here. Hey, so you got your bicarbonate ion. Guess what? Bicarbonate ion can spit out a proton and make a carbonate ion. It's got this equilibrium constant. an even smaller equilibrium constant. Can I add these two reactions together? You bet I can. I hope you remember from last semester how to add reactions up. You add up all the things on this side, add up all the things on this side. Anything you can cancel, you cancel. Oh, I have a bicarbonate ion that's on the right side of the arrows. I have a bicarbonate ion on the left. He cancels. So the overall process would be H2CO3 can react and produce 2 protons and also give a carbonate ion. That's your overall reaction when you add these two steps together. What's your value of K here? It's going to be 4.2 times 10 to the negative 7. Multiplied by 4.8 times 10 to the negative 11. And you multiply those two together, you get some really small number, 2 times 10 to the negative 17. So the equilibrium constant for this overall process is even smaller. But again, you add two reactions together, you multiply the values of K by each other. I'm going to stop here and we will do a third video showing you the last types of equilibrium calculations you have to master here.